Alright, good afternoon. This lesson is for my Honors Integrated 1 class. This is lesson for 22.3. Before I get started, I want to say I hope everybody is doing okay out there. So today, our goals are going to be about what's called the triangle inequality, and we're also going to look at side angle relationships inside of a triangle. And so I'm going to go ahead and start off with this this picture that I drew, which on its face looks like it has nothing to do with triangles. So let me tell you what this poorly drawn picture is supposed to represent. The blue is supposed to be water. This is a bridge. This is a bridge. There's a sailboat coming through what's called a drawbridge, where the parts of the bridge actually move, and there's a car waiting to proceed. So I'm originally from New Jersey, and New Jersey is surrounded by what we call barrier islands, and you have to take these very long bridges to go from the mainland to the barrier island to get to the shore. And these bridges in some places aren't built very high off the water, and boats, with their sail masts can be very tall when they're on the water, and so this created a problem because these sailboats can't go under the bridge. And so what they did is they created a system where the bridge opens up and then it flattens out, opens up, lets the boat come through, and then moves on. So to me, the idea of a drawbridge actually is quite a good way to introduce the idea of the triangle inequality. So let's just say that this boat passes through. It made it through. All right, here we go. We made it. And if a drawbridge was created correctly, what would happen is these sides would swing down, and they would meet and make a flat surface, and the car would then proceed and drive, right? So basically, if a drawbridge is done correctly, this side, this length, and this length must be the same length as the gap that it's covering, okay? Now, if somebody wasn't paying attention and they engineered the bridge in such a way where this length was shorter than this length, you would have a gap, and this would not be a very safe bridge. And that's assuming that these would stay flat. Most likely they would fall all the way through. So this length and this length are not equal to this length, and you can't cross. Now, the other possibility, the other outcome that we could have here is that this length on this side and this length on this side, they were made too long. And if they're made too long and they come down at the same rate, they meet and they form a bump, right? And this is where we get the triangle inequality idea from, because this now becomes our triangle, right? And so this is a long, kind of abstract example, but what I was trying to show you here is that in order to make a triangle, two sides must be larger than the third side, or must be longer than the third side. So that's really what this idea was meant to show us. So let's make that a point. So two sides must be longer than the third. This is our premise to make a triangle, right? All right. So, we have some random triangle, and this side length is x, this side length is y, and this side length is z. Using that idea, length x and length y must be longer than length z. And the same would be true for length x and length z. That should be longer than length y. And length y and length z must also be longer than length x. And so we get this series of inequalities from this idea that the two sides must be longer than the third. This is the triangle inequality, right? And so I'd like to actually use the triangle inequality here. Let me draw a triangle and show you how we could use this. I like to say the word a lot. If this length is 5, this length is 12, and this is going to be around. Remember, 2 side lengths must be longer than the third. So that means that I know that 5 and my unknown length must be larger than 12. And, you know, I skipped the I skipped what I was going to do here. I didn't explain what I was going to do here. So this problem, I'm going to find out what are the possible lengths. How long can this be? That would make a little bit more sense. How long can this question mark be? And the only thing that we know is that 2 sides must be longer than the third. Right? The other possible setup would be 12 and my unknown length must be longer than 5. And the third possible inequality that I can write would be 12 and 5 must be longer than my unknown length. Right? Okay, so if we if we isolate our unknown length here, we know that our unknown length, I subtract 5 to both sides, our unknown length must be longer than 7. This one's not going to make sense. This one's going to say that our unknown length has to be longer than -7, which is doesn't really do anything. And the last one is going to be that 17 is longer, or longer than our unknown length is allowed to be. And so we're going to get 3 possibilities. This one doesn't make sense, so just throw it away. Length can't be larger than negative. Well, it can be larger than negative, but it doesn't really tell us much, right? Because you would be allowed to have a length of 0, and that wouldn't make sense. So I know that my unknown length is longer than 7, but it's not as long as 17. You can actually make a compound inequality out of this. So this unknown length is allowed to be longer than 7, but not as long as 17. Okay, so that's how I would figure out how long an unknown side would be in a triangle using the triangle inequality concept. So I'm going to check that first idea off. Okay. And so now I'm going to talk about my second goal, side-angle relationships. Okay. Let me just erase everything here. All right, here we go. So I'm going to actually start off with and this is just going to be an example. I'm going to start off with a unassumed equilateral triangle, which we saw from section 22.2, that if it's an equilateral triangle, it must be an equal angular triangle. All right. And so let's keep something in mind here. All three angles are 60 degrees. Okay. And let's say for the example here that each side length has a length of 10. Okay, so each side length is a length of 10. Each angle has to be 60 degrees. That has to be, but the side length doesn't really matter. I just picked 10 because that's an easy number to look at here. So we're starting off with a triangle here. Notice all the sides are equal, so are all the angles. Okay, so now we're allowed to cut an angle in half, right? And if we bisected a 60-degree angle and we drew a line down, that means that we would be left with let me try this again. That means that we would be left with a 60-degree. This is 10. Now, I cut 60 in half, so this is 30. And this angle, they all three add up to 180 degrees, and if I have 90 of it here, that forces this to be 90 degrees. Now, all right, so let's see here. My largest angle in this triangle is 90 degrees. Opposite the largest angle is going to be the longest side, and I know that it's the longest side. I know for sure that this side has to be longer than this side, because when I bisected this, I drew a line down that cut this length that was the same as that. I cut it. So for sure this has to be longer than that. And I can even reason that this side must be longer than this side, because this side at an angle is as tall as this side, which is standing straight up. If this side was to stand straight up, it would be much taller. Right? So I know right off the bat here that opposite the largest angle is the largest side. Now, let me do something really quick. If I was to, bisect this angle, right? And now I have, I think, I bisect the angle, right? So I have this. I just made two identical little triangles, right? So because I have an angle, side, angle, that means that this must be the same as this. That forces this side to be 5. Okay? I can find this unknown side. I can find this unknown side very quickly. And I think that actually be kind of useful to see to further show the side angle relationship. So I can very quickly find this length. I know that this length squared, I would use Pythagorean theorem, and 5 squared, which is going to be 25. These two lengths together squared will add up to that length. So I get my x squared plus 5 squared, come on, I can do this, plus my 25 equals 100. And so I subtract that means I get x squared equals to 75. Let me come down here. God, I'm just making a mess out of this lesson today. We'll go over here. So that means that x squared is equal to 75. Square root. Well, I know that the square root of 75 is going to be a number that's bigger than 5, but not as big as 10. So, okay, I know it's bigger than 5. This is bigger than 5. But it's also smaller than 10. Okay, so it's longer than 5, it's smaller than 10, and the reason why I want to make that distinction and that calculation is because notice opposite the smallest angle is the shortest side. Okay. And so if I know opposite the largest angle is the longest side and opposite the smallest angle is the shortest side, then opposite the median angle is going to be the middle length, right? And so this is the side angle relationship that I want you to understand. Opposite the smallest angle is the shortest side. Opposite the longest angle is the longest side. Opposite the median angle, the angle in the middle, is going to be the length in the middle, right? The median length. So median meaning middle. Okay, no. Yeah, median meaning middle, yeah. So this is what I wanted you guys to understand about side angle relationships. We can actually use this concept to order angles. We can figure out, if we know the side lengths, we can figure out what angles we can order the angles from largest to smallest or smallest to largest. If we know the angles of a triangle, we can use that information to order the side lengths from shortest to longest or longest to shortest. Right. So again, I just took an equilateral triangle, which is equal angular, made identical triangles, and showed you that how the relationships had to work. So this finishes 22.2. Again, I hope everyone's doing okay out there. I will post the next video on Wednesday, and have a good day, everybody.